First, we're going to have an introduction to logarithms. I stayed up and wrote this last night. I got very inspired. Because logarithms and exponential functions are totally related. They're cousins. One is the inverse of the other, so they would have to be related. So the first and most important form of relationship is this. Here are our exponential functions, and here are their inverses. If you have the function 3 to the x, then the inverse function is going to be log base 3 to the x, and 3 is written down here beside the g, but down beside the g. 7 to the x, the inverse is log base 7 of x. For 10 to the x, it's a little bit different. This is just log x. The 10 that would normally go right here is understood. We don't actually write it most of the time. Almost all the time, but I'm sure there are some times when you do. And now here might be the most difficult to get used to. First, E is a number. It's about 2.7, but it really goes on forever. The decimal part goes on forever. Its inverse is the ln of x, the natural log of x. But what the ln of x really is log base e of x. But somebody decided, hey, I don't want to write log base e. Actually, what I heard was it was a group of scientists, and they said, look, we use these logarithms all the time. So let's have just ln, okay, the natural logarithm. And so we'll take log base e, we'll save our hands from writing a lot, and have log base e just be ln. Okay, now, this, I mean, we may have gone over this before. I teach this in so many classes, it's hard to remember where I've said it and where I haven't. This part is called the argument of the function. Where the x is the argument. Yes, when we were graphing with transformations, we talked about the argument. The argument is where horizontal motion is. Left and right. Okay, so that's the basic relationship. You can come up with any base. If you wrote f of x equals 2 to the x, then the inverse function would be log base 2, see, it's the same base, of x. And there's the x. Actually, no, because, no. That'll be explained later, but the 2 and the 2 show that they are inverse functions. Okay, now you have to imagine, I mean, it helps if you can imagine. We're down here on this level with the bases, and when we see an exponent, we say, oh, that's moved up. But when you're dealing with logarithms, you're really up here on this level, looking down at the bases. So it's a different experience, but the same math that governs exponents will govern logarithms, because logarithms are exponents. Hard to believe, but true. So here's what's happening. You remember these rules, I'm sure. You might not have memorized, but you do remember that we went over them in this class. We've gone over them in previous classes. These are the rules of logarithms. If you multiply exponents, if you multiply x to the 3 times x to the 2, just for instance, if the bases are the same, then you can write this with one base and add the exponent. So when you multiply like bases, you add the exponents. When you divide like bases, you subtract the exponents. When you have a base and you raise it to a power and you raise it to a power again, you multiply the exponents. And the zero power rule is that any number raised to the zero power is 1. And the power 1 rule is that any number raised to the 1 power is just the number itself. There are similar rules in logarithms, but they're from the perspective of the exponents. So the product rule for logarithms is that, now these are just for instance numbers. These numbers are not important in and of themselves. I just chose them. Log base 3 of 14 plus log base 3 of 2. This is addition. But when you add two logarithms that have the same base, what you do is you multiply the arguments. So these two logarithms added together are going to equal log base 3 of the arguments multiplied, 14 times 2, which is log base 3 of 28. Nothing special about those numbers. Okay, when you, okay, here's the quotient rule for exponents. When you have like bases, when you divide like bases, you subtract the exponents. Here, we have log base 17 of a fraction, 5 over 14. What that equals is log base 17 of 5 minus log base 17 of 14. So you take log base 17 of the top and divide and subtract log base 17 of the bottom. The equivalent of the power rule for logarithms, here x to the 2 and then raised to the 3 is x to the 2 times 3. Well, here we have it with the ln. The ln, the natural logarithm, is just a logarithm, has the same rules. The ln of x raised to the 3, you bring the 3 down in front. That will be 3 times the ln of x. We can also write this with what are considered normal logs. How about log base 5? Log base 5 of x to the 3rd equals 3 times log base 5 of x. You have to learn it, you have to memorize it, you have to get flashcards or whatever helps you memorize. All right, the equivalent of the zero power rule. Zero power is 1. Any number raised to the zero power is 1. Well, let's take log base 9 this time. Again, it's not important. Log base 9 of 1 is 0. In fact, the ln of 1 is 0. Log to any base of 1 is 0. You can count on it. Name a log, any miscellaneous log. How about log base 384? Log base 384 of 1 is 0. Imagine. Okay. Now the power rule of 1, here it is. Log base 3 of 3 is 1. Log 10 is really log base 10. But again, we don't write it. Log base 10 of 10 is 1. The ln of e is 1 because the ln of e is really log base e of e. Since those two numbers are the same, the answer is going to be 1. Anytime you see the base and the argument being exactly the same, the answer is 1. Now we're going to go through the steps of finding the inverse of a function. Remember, let's find the inverse of 3x plus 5 first, just to help remind you of the steps. 3x plus 5. First, you change f of x to y. Then you switch the x's and y's. Then you solve for y. So subtract 5, subtract 5. That'll give us x minus 5 equals 3y. The 5 minus 5 zeros out. Then divide by 3, so that y equals x minus 5 over 3. And what this means is that the inverse function of f of x, which is written f inverse, ugly f inverse of x equals x minus 5 over 3. This has nothing to do with the exponents over here, except we're going to use the same 4 steps to find the inverse of f of x to the 5, f of x equals 5 to the x power. This is an exponential function. So step 1, we change f of x to y, so that we have y equals 5 to the x. Step 2, switch the x and the y. X equals 5 to the y power. Now step 3 is what took mathematicians, professional mathematicians at the major universities of Europe, hundreds of years in the Middle Ages and into the late Middle Ages and into the Renaissance. Remember your world history there. They just couldn't do it. They couldn't find out how to solve for y in this case. Nothing worked. And then the answer was found by accident, by someone who was working on something else. Anyway, here's step 3, where we solve for y. Y equals log base 5 of x. So the inverse function of f of x is log base 5 of x. That's what a logarithm is. We are going to spend the day going back and forth and back and forth, and I need to add another page right now so that I can scroll this up where you can see better. So it doesn't even matter what it looks like really, but there. Okay, there now. Here we go. We're going to spend the day today doing what I'm about to do right now. Log base 7 of 49 equals 2. This is a logarithmic function. But why? I mean, this is really true. That log base 7 of 49 equals 2. How do I know? Because, watch this. The base 7 raised to the 2 power equals 49. You can switch back and forth between exponential functions and logarithm functions and logarithm functions and exponential functions because this is always, always, always going to be true, and that's what this symbol means. It means it goes beyond equal to total equivalency. A log has a base down here, an argument up here, and it ends up that this is the exponent. The exponent of what? Log base 7 of 49 equals 2. 2 is the exponent of the basic exponential function 7 raised to the 2 power, here's the exponent, equals the argument. The base raised to the exponent equals the argument. Now this is the most important thing that you might need to learn in this part of the semester, is that you can switch these back and forth just by remembering where the words go. Okay, so you already know what it's like to see the base raised to an exponent equals, oh, how about just, let's not do that. How about this? How about something you know? You know this so well, you could do it in your sleep. 3 to the 2 equals 9. Everybody knows that. But you can change this to a logarithm by remembering where the words go. Log, base goes down here. Exponent goes out here. I found it's easier to remember those two. Well, what's left over goes here, and what's left over is the argument. So the base is 3. The base is holding up the exponent. This is going to be, or here, let's do this. Totally equivalent. All right, log. The base goes down here. The exponent goes over here. That leaves that. That's going to go here, and we call this the argument. Arg, matey. All right, so we're going to spend the day doing this. This is just a review, a very brief review of what logarithms are. Now it's not a review of what you know before, because anything that's being reviewed here is the exponential part. You have studied this for 2 semesters, even if you don't remember it, you have. You studied it before you got to college algebra, and then you studied it when you got into college algebra. But you haven't studied what the matching logarithms are. This may be the first time for most of you. I would recommend reading over this over and over and over and over and over. And really, flashcards are so cheap. Go over to Walmart, go to Target, go to wherever, order them from Amazon. Make your own. But put this stuff on flashcards and look at it every day. Okay. Make your own. Write them with your hand.